Selective coordination for emergency and standby systems is required by the National Electrical Code, specifically Article 700 and 701 in the 2005 edition. This requirement ensures that during a short circuit, the circuit breaker nearest to the fault trips first, isolating the problem while maintaining operation in the remaining circuits. When dealing with parallel circuit breakers feeding emergency or standby loads, selective coordination is essential to ensure that the standby load is disconnected first in the event of a short circuit. There are several methods to achieve selective coordination with parallel circuit breakers. One method involves using circuit breakers with a magnetic-only trip unit in parallel with an overcurrent device that has a time delay. The magnetic-only trip will quickly respond to high-magnitude faults, while the time delay prevents unnecessary tripping from smaller overloads. Another approach is to install peak-limiting circuit breakers in parallel with a solid-state trip unit. Peak-limiting circuit breakers restrict the peak let-through current, which prevents other breakers from tripping on smaller faults. A third option involves using current-limiting circuit breakers, which prevent high peak currents from flowing downstream. This ensures that the breaker closest to the fault will trip. For a specific case involving an existing 150 amp circuit breaker, a 400 amp circuit breaker, and a new 250 amp circuit breaker for a standby load, it is recommended to install a 250 amps current-limiting circuit breaker for the new standby load. Additionally, install a 400 amps magnetic-only trip circuit breaker for the existing emergency load. If the existing 150 amp circuit breaker is not already a magnetic-only trip type, consider installing a separate overcurrent device with a time delay in its place. After installing the circuit breakers, it is crucial to conduct a selective coordination study to confirm that the system operates as intended. This study should simulate various fault scenarios and demonstrate that the standby load breaker trips first for all faults within its downstream circuit. This verification process is vital to guarantee the reliability and effectiveness of the emergency and standby power systems. The goal of selective coordination is to minimize the impact of faults by isolating them quickly and efficiently. This is accomplished by carefully selecting and coordinating circuit breakers to ensure that only the breaker closest to the fault opens, leaving the rest of the system operational. Firstly, consider the available fault current at various points in the system. This requires a short circuit study to determine the magnitude of fault current that each breaker might need to interrupt. Secondly, review the time current curves of the circuit breakers under consideration. These curves illustrate the time it takes for a breaker to trip at different levels of overcurrent. Selective coordination is achieved when the time current curve of the downstream breaker lies entirely to the left of the time current curve of the upstream breaker. Thirdly, look into current limiting breakers. These breakers limit the amount of fault current that flows through them, reducing stress on downstream components and improving coordination. Fourthly, consider using zone-selective interlocking. This advanced feature allows breakers to communicate with each other, enabling the breaker closest to the fault to trip quickly while preventing upstream breakers from tripping unnecessarily. Fifthly, implement proper maintenance and testing. Regularly inspect and test circuit breakers to ensure they are functioning correctly and that the settings are appropriate. Sixthly, document all coordination studies and settings. Keep a record of the coordination studies performed, the settings used for each breaker, and any changes made to the system. Seventhly, be aware of the impact of motor starting currents. Motor starting can cause temporary overloads that could potentially trip breakers. Ensure that breakers are selected and set to accommodate motor starting currents without causing nuisance trips. Eighthly, understand the limitations of selective coordination. In some cases, it may not be possible to achieve perfect selective coordination due to the characteristics of the breakers or the configuration of the system. Ninthly, consider the impact of arc flash. Selective coordination can help reduce arc flash hazards by minimizing the duration of faults. Conduct an arc flash study to assess the potential hazards and implement appropriate mitigation measures. Tenthly, stay up to date with the latest codes and standards. The NEC and other relevant standards are constantly evolving, so it is important to stay informed about the latest requirements for selective coordination. In addition to the previously mentioned points, it is also essential to understand the specific requirements outlined in Articles 700 and 701 of the National Electrical Code. These articles provide detailed guidance on the design, installation, and testing of emergency and standby power systems, including the requirements for selective coordination. Emergency systems are intended to automatically supply illumination, power, or both, to designated areas and equipment in the event of failure of the normal supply or when the normal supply voltage is unacceptably low. Standby systems may supply power to loads that are not necessarily critical for safety, but are essential for business operations or other purposes. Selective coordination is particularly important in emergency and standby systems because a failure in one part of the system should not cause a complete shutdown. By selectively coordinating the circuit breakers, it is possible to isolate faults and maintain power to critical loads. When designing a selectively coordinated system, it is important to consider the ratings of all the circuit breakers and other overcurrent protective devices. The breakers should be sized to carry the normal load current, but also have sufficient interrupting capacity to safely clear any potential fault currents. The time current curves of the breaker should be carefully coordinated to ensure that the downstream breaker trips before the upstream breaker. In some cases, it may be necessary to use different types of breakers to achieve selective coordination. For example, a current-limiting breaker may be used to protect a sensitive electronic load, while a magnetic-only breaker may be used to protect a motor circuit. It is also important to consider the impact of voltage drop on the performance of the emergency and standby systems. Excessive voltage drop can cause equipment to malfunction or fail, so it is important to ensure that the conductors are properly sized and that the voltage at the load is within acceptable limits. Regular testing and maintenance are essential to ensure the reliability of emergency and standby power systems. Circuit breakers should be inspected and tested regularly to verify that they are functioning properly. Batteries should be checked to ensure that they are fully charged and in good condition. Generators should be exercised regularly to ensure that they will start and run reliably when needed. Finally, it is important to have a well-documented emergency plan that outlines the procedures to be followed in the event of a power outage. The plan should identify the critical loads that need to be powered by the emergency or standby systems, and should specify the steps to be taken to restore power to those loads as quickly as possible. The plan should also include provisions for training personnel on the operation and maintenance of the emergency and standby power systems. By following these guidelines, it is possible to design, install, and maintain reliable emergency and standby power systems that will provide essential power during a power outage. Remember that selective coordination is not a one-size-fits-all solution, and the best approach will depend on the specific characteristics of the system. It is essential to work with qualified electrical engineers and contractors to ensure that the system is properly designed, installed, and tested. By understanding the principles of selective coordination and following the requirements of the National Electrical Code, it is possible to create electrical systems that are both safe and reliable. This also includes taking into account any modifications or changes in the electrical loads or system configuration. Any alterations can affect the coordination between circuit breakers and necessitate a review and update of the selective coordination study. It is important to view selective coordination as an ongoing process rather than a one-time task. This proactive approach ensures the continued reliability and safety of the electrical system, especially in critical applications such as emergency and standby power systems. Furthermore, consider the environmental conditions in which the circuit breakers and other overcurrent protective devices are installed. Temperature, humidity, and altitude can all affect the performance of these devices. Make sure to select devices that are suitable for the specific environmental conditions and to follow the manufacturer's recommendations for installation and maintenance. Also, consider the available space for installing the circuit breakers and other overcurrent protective devices. In some cases, it may be necessary to use compact circuit breakers or other space-saving devices to fit within the available space. However, It is important to ensure that these devices meet all the applicable requirements for selective coordination and that they are properly installed and maintained. Remember that selective coordination is not just about selecting the right circuit breakers. It is also about properly installing and maintaining them. Make sure that all circuit breakers are properly labeled and that their settings are clearly marked. Train personnel on the proper operation and maintenance of the circuit breakers and other overcurrent protective devices. By taking these steps, you can help ensure that your electrical system is safe, reliable, and selectively coordinated. Finally, remember that selective coordination is a critical aspect of electrical safety. It helps to protect people and equipment from the hazards of electrical faults. By understanding the principles of selective coordination and following the requirements of the National Electrical Code, you can help to create electrical systems that are safe and reliable. Understanding the specific characteristics of each type of circuit breaker and how they interact is crucial for effective selective coordination. For example, inverse time circuit breakers have a tripping time that is inversely proportional to the current. This means that they trip faster at higher current levels. Current limiting circuit breakers, on the other hand, limit the amount of fault current that flows through them, reducing stress on downstream components. Magnetic-only circuit breakers trip instantaneously when the current exceeds a certain threshold, regardless of the duration of the overcurrent. Each of these types of breakers has its own advantages and disadvantages, and the best choice will depend on the specific application. In addition to the type of circuit breaker, the settings of the breakers are also critical for selective coordination. The settings determine the current and time at which the breaker will trip. These settings must be carefully coordinated to ensure that the downstream breaker trips before the upstream breaker. The process of setting the breakers typically involves consulting the manufacturer's time current curves and performing calculations to determine the appropriate settings. It is important to note that selective coordination is not always possible to achieve perfectly. In some cases, the characteristics of the breakers or the configuration of the system may make it difficult to coordinate the breakers effectively. In these cases, it is important to consider other protective measures, such as arc flash protection, to mitigate the hazards of electrical faults. Furthermore, it's important to consider the impact of harmonic currents on selective coordination. Harmonic currents are non-sinusoidal currents that can be generated by electronic devices such as computers, variable frequency drives, and LED lighting. These currents can distort the voltage waveform and cause circuit breakers to trip prematurely. To mitigate the impact of harmonic currents, it may be necessary to use harmonic filters or to select circuit breakers that are specifically designed to withstand harmonic currents. It is also important to consider the impact of ground faults on selective coordination. A ground fault occurs when current flows from a live conductor to ground. Ground faults can be very dangerous and can cause severe electrical shock. To protect against ground faults, it is necessary to use ground fault circuit interrupters, or GFCIs. GFCIs are designed to detect ground faults and to quickly trip the circuit breaker, preventing electrical shock. In addition to GFCIs, it is also important to use properly grounded equipment. Grounding provides a low impedance path for fault current to flow back to the source, which helps to trip the circuit breaker and clear the fault. It is also important to use surge protection devices, or SPDs. SPD are designed to protect electronic equipment from voltage surges, which can be caused by lightning strikes, power outages, or other events. Voltage surges can damage or destroy electronic equipment, so it is important to use SPD to protect against these surges. When selecting SPD, it is important to choose devices that are properly rated for the voltage and current levels of the electrical system. It is also important to consider the location of the SPD. SPD should be installed as close as possible to the equipment that they are protecting. Proper documentation and labeling are also essential for maintaining a selectively coordinated system. Accurate records of breaker settings, coordination studies, and any system modifications should be readily available. Clear labeling of breakers and equipment helps ensure that personnel can quickly identify and respond to any issues. Regular training for electrical personnel is crucial to ensure they understand the principles of selective coordination and can properly operate and maintain the system. Training should cover topics such as breaker types, settings, coordination studies, and troubleshooting. This understanding allows for quick identification of issues, appropriate responses, and minimization of downtime. The coordination study should involve a detailed analysis of the electrical system, including the source impedance, conductor sizes, and load characteristics. The study should also consider the potential fault currents at various points in the system. The results of the coordination study should be documented in a written report that includes recommendations for breaker settings and other protective measures. This report should be kept on file and readily available for reference. When making changes to the electrical system, such as adding new loads or modifying existing circuits, it is important to review the coordination study to ensure that the selective coordination is maintained. Changes to the system can affect the fault currents and breaker settings, so it is essential to update the study and make any necessary adjustments. In addition to the technical aspects of selective coordination, it is also important to consider the human factors. The electrical system should be designed and operated in a way that is safe and easy for personnel to use. Breakers should be clearly labeled, and operating procedures should be well documented. Personnel should be trained on the proper use of the electrical system and the potential hazards of electrical faults. This focus on human factors helps to reduce the risk of accidents and injuries. Selective coordination is a crucial aspect of electrical safety, but it is just one part of a comprehensive electrical safety program. A comprehensive program should also include measures such as arc flash protection, ground fault protection, and surge protection. By implementing a comprehensive electrical safety program, you can help to protect people and equipment from the hazards of electrical faults.